in previous videos on improper integrals, I explained what are the two different types of improper integrals, and when we say that improper integral converges at left hand, converges at right hand. Now, the general case, improper integrals, general case means consider integral a to b f of x dx. Suppose it is improper. Suppose it is improper. It is improper integral of second kind because function is unbounded in AB. It is unbounded. Limits are finite. Function is unbounded. Now, in this case, suppose there are finite number of points of discontinuities. Let C1, C2, C3, etc. Cn be n number of discontinuities. Then it is called general case. There are n number of discontinuities. Then how to discuss the convergence? We write integral a to b fx dx as a to c1 fx dx plus c1 to c2 fx dx plus so on integral Cn minus 1 to or Cn to b fx dx. Then we discuss the convergence of all these integrals using the definitions that I had given earlier. If all these integrals converge, then we say that improper integral converges. Now this is called general case. Let us consider examples of general case later. I give one more definition now. Definition of first type of integral, that is improper integral converging at infinity. Convergence at infinity it is called. Convergence at infinity. Suppose I explain. Suppose fx is bounded and integrable in a to t, where t is greater than or equal to a. Then integral a to t fx dx is proper. Fx dx is proper. Suppose fx is bounded and integrable in a to t, and t greater than or equal to a here, a to t fx dx is therefore proper. Proper means it exists. We assume that every proper integral exists. Then, if limit a to t f of x dx as t tends to infinity exists. Say, if limit a to t fx dx exists as t tends to infinity, then we say that integral a to infinity f of x dx converges. Therefore, to test a to infinity fx dx for convergence, first we write a to t fx dx at t tends to infinity, where a to t fx dx is proper, and we take limit of this as t tends to infinity. If it exists, then we say that a to infinity fx dx converges. That is convergence at infinity. On the other hand, how to test the convergence at minus infinity? For that, convergence at minus infinity. Here, as given like this. Suppose fx is bounded and integrable in t to b. See here, difference t to b, where t is less than or equal to b. Then integral t to b f of x dx is proper. And we know that every proper integral exists. We assume that every proper integral exists. Now this t to b fx dx is proper, therefore exists. If limit integral t to b f of x dx as t tends to minus infinity exists, then we say that the improper integral minus infinity to b fx dx exists. Definitions are similar. A to infinity fx dx. When you say that a to infinity fx dx converges, if limit a to t fx dx as t tends to infinity exists, where a to t fx dx is proper. Similarly, we say that integral minus infinity to b exists if limit t tends to infinity t to b fx dx exists. These are the definition. So if you understand the definition, and then you can easily solve the problems. Now first type of problems are based on only definitions here. Definitions. I consider examples also. Example, test the convergence of problem 6. First problem is 0 to infinity dx by 1 plus x square. Second, 1 to infinity dx by x square. See, without knowing the convergence of the integral, or even without knowing whether they are what type of integrals, improper, without knowing they are improper, you have calculated such integrals. Now you come to know that this type of integrals are called improper. And how to test the convergence? Now these two are converging at infinity. That means not converging at infinity. The improper integral of first kind there. First kind. Now when we say that this converges, we write pi of t is 0 to t dx by 1 plus x square. We write pi of t is this. Now what is primitive here? Dx by 1 plus x square? Tan inverse x from 0 to t. Therefore it is tan inverse t minus tan inverse 0. What is tan inverse 0? Tan inverse 0 is 0. Therefore pi of t is tan inverse t. Now if limit pi of t tends to infinity exists, what is this? Tan inverse infinity. And tan inverse infinity is pi by 2. So it is finite, it is pi by 2. We say that integral 0 to infinity dx by 1 plus x square converges. That is the definition. Converging at infinity. Converging at infinity. Similarly, second problem. Consider 1 to infinity dx by x square. We write pi of t is 1 to t dx by x square. Obtain the primitive. How do you integrate? What is integration of 1 upon x square? Simple it is. It is x raised to minus 1 minus 2 plus 1 upon minus 2 plus 1 from 1 to t. So minus 1 upon x from 1 to t, or it is minus of 1 upon t minus 1, or 1 minus 1 upon t. Now take limit. Consider limit pi of t tends to infinity. It is limit t tends to infinity of 1 minus 1 upon t. As you know that as t tends to infinity, 1 upon t becomes 0, it is 1, which is finite. So what is the conclusion? This implies 1 to infinity dx by x square converges. See, here we are not calculating the value of the integral, and only we test whether the integral converges or not. These are some examples. Now next type is, consider integral minus infinity to infinity f of x dx. Next type, we have taken converging at infinity, minus infinity, but now minus infinity to infinity fx dx. In this case, we take c as any point, c be any point which is any real number, and we write minus infinity to infinity fx dx as fx dx is minus infinity to c fx dx plus c to infinity fx dx. Now this is converging at minus infinity, converging at infinity. We have discussed this type, converging at infinity, converging at minus infinity. If both these two converge, then we say that improper integral converges. Now we consider next case. It is called general case. General case means the limits are infinite, and also function is unbounded. Limits are infinite, function is unbounded. This is called general case. Consider minus infinity to infinity fx dx. Here there may be some points of discontinuity also. What do you mean by points of discontinuity? If function is unbounded in some in between minus infinity to infinity, that means function is unbounded at some point, then it is not bounded in any neighborhood of that point. That is called point of discontinuity. Here there may be some points of infinite discontinuities. Infinite discontinuity. That is C1 there may be some points of infinite discontinuities. Then what happens? We enclose these discontinuities in the interval AB. In the interval AB. So this is the general case. It is called mixed type of infinite discontinuity, the infinite integrals, because range is infinite, also function is unbounded. Range is infinite, it consists of some infinite discontinuities also, function is unbounded also. Then we consider that infinite discontinuities, or we enclose that discontinuities in a interval AB. Then we write minus infinity to infinity fx dx as minus infinity to a fx dx plus a to b fx dx plus b to infinity fx dx. correct? Minus infinity to a to b, b to infinity. Now we have enclosed infinite discontinuities in AB. Here in between AB there may be again points of discontinuities. Then we write that as A to C1. Suppose C1, C2 are discontinuities. We write this as A to C1 plus C1 to B. If both these two exist, then A to B exists. And when you say that minus infinity to A fx dx exists, if limit t tends to minus infinity of t to a fx dx exists, if limit t tends to infinity of b to t fx dx exists, then these two exist. And if this also exists, we say that the improper integral minus infinity to infinity fx dx exists. This is most general case. What do you mean by general case? General case means limit is infinite as well as the function fx is unbounded. Here the procedure is we enclose all the infinite discontinuities in a closed interval AB, and we write minus infinity to infinity as minus infinity to a to b, b to infinity. Here in between a and b there may be finite number of discontinuities, C1, C2, etc. Cn. Then we write a to C1, C1 to C2, C2 to C3, Cn to b. If all these exist, then we say that improper integral converges. This is called general case. Now I have discussed all the cases: discontinuity, infinite integrals of first kind. Improper integrals are also called infinite integrals. Improper integrals are also called infinite integrals. I have taken infinite integrals of first kind, second kind, mixed improper integrals. Now let me consider problems. First is, consider this problem: examine the convergence of 1 to infinity dx by x into 1 plus x. It is also first type of problem. First type means primitives can be easily obtained. Here primitive can be easily obtained. We consider the problems where the primitives cannot be easily obtained. That is, for that we require certain tests. We are dealing with only first type of problem here. And study the nature of integral here. It is improper. Why it is improper? Function is bounded here. There is no point of discontinuity in between 1 and infinity. X greater than 1, function is bounded. Here function is bounded. Function is bounded for all x greater than or equal to 1. There is no points of discontinuity, and we write pi of t is, when do you say that 1 to infinity dx by x into 1 plus x exists? If limit pi of t 1 to t dx by x into 1 plus x as t tends to infinity exists. So we write pi of t is 1 to t dx by x into 1 plus x. Now to find the primitive we use partial fraction, and 1 upon x into 1 plus x, it is easy to write into partial fractions, resolve into partial fractions. You can easily write this as, it is 1 upon x minus 1 upon 1 plus x, because 1 plus x minus x cancels, 1 upon 1 plus x. Am I right here? You need not take a by x, b by 1 plus x. You can directly write here 1 upon x into 1 plus x is 1 upon x minus 1 upon 1 plus x. Therefore, pi of t is integral 1 to t 1 upon x minus 1 upon 1 plus x dx. It is log x minus log 1 plus x from 1 to t. Now we use a property of logarithms, x by 1 plus x 1 to t, x by 1 plus x. Now first write what is pi of t here. It is log of t by 1 plus t t by 1 plus t minus log of 1 by 1 plus 1, because x is t, x is 1. Therefore it is pi of t is log of t by 1 plus t minus log half. Now take limit t tends to infinity of pi of t. It is limit t tends to infinity of log of t by 1 plus t minus log half can be written as plus log 2. These are some elementary properties of logarithms. Plus log 2. How do you evaluate this limit? Limit t tends to infinity log of 1 divided by 1 upon t plus 1 it is, plus log 2 divided by t here. Because always to take limit as t tends to infinity, we use 1 upon t tends to 0. 1 upon t is 0. So what is this? Log 1. 1 upon t is 0 plus log 2. But what is log 1? Log 1 is 0. So this is, as t tends to infinity, it becomes log 2. It is finite. This implies integral. What was that integral? 1 to infinity, yes, 1 to infinity dx by x into 1 plus x converges. This was a simple problem. Next I take some more examples. I consider that in the next video, some problems and some more concepts, practical comparison test and so on. Yes, thank you.